Hello, in this video we're going to look at Rolle's theorem and the mean value theorem. And we'll use Rolle's theorem to prove the mean value theorem. But first, Rolle's theorem. Let's let f be continuous in the interval, closed interval a to b, and suppose that f of a and f of b equals 0, equals each other. Then if the derivative exists in the open interval a to b, there exists a point C in the interval a to b such that the derivative at C is 0. And this is sort of a picture of what I think it is. So a and b, f of a and b equals 0, and then the function does something and comes up, but at some point on this graph there's a derivative with 0. Now you could also draw this going down. Well, it can go down and then up, and as long as there's 2 points here, then there's at least one C where the derivative is 0. So let's assume that there exists an x in AB such that f of x is greater than 0. So we're going to assume that at some point it goes positive. Now the proof is very analogous when we assume that it's less than 0 when it goes down. By the extreme value theorem, there exists a C in the interval AB such that f of C is a maximum. Now this is one of those things where at some point you have to assume things are true. So the extreme value theorem essentially says if you have a continuous function in the closed interval a to b, it assumes some maximum and some minimum. You know, it's a finite value. And so we're going to let C be the point in the interval such that f of x attains its maximum. Now we're going to prove Rolle's theorem by contradiction. So first let's assume that the derivative at C is greater than 0, right? Our goal is to prove it's 0. Then, you know, the derivative of f at C is defined by this, and we let h go to 0. Now remember, h go to 0 means it goes to 0 from the positive numbers, or it goes to 0 from the negative numbers. So both have to be true for this to be true. But if we assume that h is positive, meaning it's going to 0 from the right, then h is positive, so we can multiply it over. Then we have this difference is greater than 0, but if we subtract that over, we get this quantity here. F of C plus h is greater than f of C. But that's a contradiction because f of C is the maximum. And so this can't happen. So thus, we know that the derivative at C is less than or equal to 0. All we have shown is that it's not positive. So next, let's assume that it's less than 0. And we're going to prove by contradiction again. Then if if h is negative, meaning, you know, because it has in this quantity, so now we're assuming that it's less than 0. And if this is negative, then we multiply it up, and then the sign switches, so it's back to this way, and then we subtract that over. And again, we have this case, which is a contradiction because f of c was the maximum, but we're saying that is, you know, this is bigger than that, so it's a contradiction. So we know that it's not greater than 0, and we know that it's not less than 0, so therefore it must be 0. Now, there's a similar argument if we assume that it's, you know, f of x goes below 0. So notice here, we assume that f of x went positive, so it went above the graph. But if it goes below, you know, for x in AB, we'll again use the extreme value theorem, and the minimum, you know, the extreme value says that there is some value in there that f achieves its minimum. And also, if f of x stays 0 for all x in this interval, then it's trivially true because the derivative of a constant function is 0, and so therefore it's always true. And that's the proof of Rolle's theorem. Now the mean value theorem is this. let's let f of x be continuous in the closed interval a to b. Suppose that the derivative exists in this open interval a to b, then there exists a point C in this interval a to b such that the first derivative at C equals this ratio. And if I were to try to draw a picture of that, this would be my attempt. So here's A and here's B. It's this is our function that's continuous. And the slope here, there's some point along here that makes has an equal slope to this, but slope is derivative, so the derivative of f at C has that same slope. So now we're going to let g be this function here, and I find this quite fascinating, because if we were just to run a regression line between this point and this point, so 2 points, it would be this line right here. Or if you just, find the equation of a line that goes through those 2 points, it's this right here. So note that if we plug in a to g of x, which is here, and then plug in a here and a here, so that makes this 0 and this is 0, so it's 0. Now if we plug in b to here, and here, then those cancel, leaving f of b minus f of b, f of a minus f of a, which is 0. So these satisfy, well, we're close to satisfying Rolle's theorem. Now, a note that since f is continuous, that's part of the assumption. And look, that's a constant. Here's the only other function, and x is continuous, so the addition of 2 continuous functions is continuous, so g of x is continuous, right? And the same way with differentiable functions. So we're assuming that f is differentiable, and we know x is differentiable, and these are all constants. So the addition of differentiable functions is differentiable. So g is differentiable. Now g satisfies Rolle's theorem. So thus there exists a c in the interval a to b such that the derivative of g at c is equal to 0. So that says that if we take the derivative of g and plug in c, which is this equation, right? So we take the derivative here, that's a constant, and then if we multiply this into each of those, this second piece goes away because it's a constant. The derivative of x is just this piece, which is this. So it equals 0 by the Rolle's theorem. But if we take this to the other side, boom, that satisfies the equation and the theorem is proved. Now let's look at a quick example. And I'm running out of paper, so I wrote it a little smaller. I apologize. We want to show that the sine of x minus the sine of y, or the absolute value of that, is always less than or equal to the absolute value of x minus y. And you might think, well, how's that? How are we going to do that in the context of the mean value theorem or Rolle's theorem? Well, if we let f of z equal sine of z, and let's just assume that x is less than x, these are real numbers, then f satisfies the mean value theorem. It's continuous, it's differentiable in any interval. So that says there exists a c in the interval x to y such that the derivative of f of c is equal to this ratio. So plug in f of x, f of y, divided by x minus y. And so this is true. But we know what the derivative of f is. It's cosine, right? So this is the cosine evaluated at c. So if we multiply this to the other side, we get this equation here. Now let's take absolute values on both sides, and we get this. But since c is always the absolute value of c is always less than or equal to 1, let's just plug in 1 that makes it a little bit bigger. And this is what we wanted to show. Yep, boom, done. Now note also that if we let y equal 0, that says that the absolute value of x is always greater than or equal to sine of x, which is kind of an interesting inequality that we all use. Well, anyway, that's all I have for today. Hopefully you enjoyed that. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.